So now let's come back to quantum gates. And then in the previous class, I think we stopped at how to express the state of a single qubit, on a graph, right? Using and we kind of, I think we end here, is that the state, okay, can be described by a coefficient in front of the ground state, which is a real number because the only thing that matters is the relative phase between the ground state and excited state, and then also the amplitude of the second of the excited state, and then the relative phase between them. Okay. And then also we say that, okay, it looks like there are 3 parameters, but then because each state has to be well normalized, so that you have amplitude square of alpha plus amplitude square of beta equals 1, right? So in fact, you only have 2 free variables. And then last time we say that if you ignore the phase term, then what this is actually a circle, right? In the 2D coordinate, right? You can call this alpha, and this is beta, and then the point on this circle represent alpha and beta. Okay, that satisfy this condition. And then now, if we add in the phase term here, you can imagine now there are actually 2 free parameters here, and then there's you can think there are 3 parameters, but then there's 1 constraint. So that naturally, what you can expect is that this is no longer a circle, but it becomes a sphere in 3-dimensional space. Okay, so let's see. Okay, so similar to a circle, right? To express a circle, the position of a circle, easy way to do is to define an angle, right? From 0 to 2 pi, using this angle to represent any point on this circle. And the same apply to the sphere. Okay, what you can do is that you can define 2 angles, right? Just like the spherical coordinate. Right, you can define this is theta, okay, and then you can define, okay, a phi. Right, these 2 angles would determine one position on your sphere. Okay, now let's see how we can use this to express our single qubit state. Okay. So one thing we notice is that alpha squared times beta squared equals 1. And you can kind of see that this is the same as sine squared plus cosine squared, right, equals to 1. Right, so you can use this to express alpha and beta. And then the way that we do it is let alpha equal to cosine theta divided by 2. Okay, and then beta equal to sine, okay, theta divided by 2. Right, so this makes sure that the alpha squared plus beta squared equal to 1. And then for the phase, okay, we just let it to be the phase here, phi. Okay, just let it to be the phase phi here. So that what this would get us is your state psi will equal to cosine theta divided by 2, okay, and then ground state plus sine theta divided by 2 e to the I phi 1. Okay, so by knowing theta and phi, you will know the entire information of your quantum state, of your single qubit state. Okay, and then I think just for a few examples, okay, probably we want to know where 0 is and where 1 is on this sphere. This is called Bloch sphere. And you can think, okay, for if psi equals ground state, that means theta is 0, right? So cosine theta is 1, sine theta is 0, right? So you return to this. So you can see that this top point, the north pole, is ground state 0, okay? And then for the excited state, 1, okay, you can see that unique cosine theta divided by 2 goes to 0, so that your theta, okay, is pi, right? So that pi divided by 2 is, and then cosine is 0, and then sine, this goes to 1, right? So that this, the south pole is 1, okay? And this is important. Why we need to show this is that you see that 0 and 1, they are orthogonal to each other, right? But on this Bloch sphere, okay, they are actually geometrically, they are not orthogonal. Okay, the 0 is pointing this way, and then 1 is pointing this way. Okay, so actually in the Bloch sphere, any two vectors that are pointing to opposite direction are actually orthogonal to each other. Okay, you no longer look for 90-degree angle between them. Okay, and so the Bloch sphere is actually used a lot, by physicists to represent the single qubit. And later in your homework and then in your exam, okay, you'll be asked to, point out, okay, where give you a qubit and then you point out, okay, where it is on the Bloch surface, Bloch sphere. Any questions? Okay, then we can move on to the next thing that's related to Bloch sphere is that if we know that the qubit pointing towards opposite direction is orthogonal to each other, then you can see that from the Bloch sphere there are numerous set of orthogonal states, right? For example, I can point it towards this way. We can call it psi 1. Okay, we can point it this way, and then we can point psi 2, and then you will see that psi 1 and psi 2, they are orthogonal to each other. So what it means is that for any quantum system, there's more than one way to define your qubit basis, right? You don't have to always define 0 and 1, okay, as your basis, as your computing basis. You don't have to always do that, okay? Just like you don't have to use 0 and 1 in your voltage in classical computer to compute. You can actually define other values, okay? And one very common set one very common qubit basis is actually what you have already seen, is that let me see, this superposition state. Okay. Okay. You guys notice this? This is the maximum superposition state, right? Well, not maximum. They're the equal weight superposition state, and then this can be get from using hammer gate on, I think, on 0. This is use hammer gate on 1, right? And then you can get these two. And then why these two are actually important is because if you think about it, is that the way that you choose the basis is that you want to be able to measure on this basis, right? For example, if you choose in the quantum well, then I wouldn't choose this basis because there's no way I can measure half of the energy, right? Because if you think about it, what this state represent. But interestingly is that for photon, okay, if you use polarization, as your basis, polarization as your as the attribute to carry your quantum information. So for photon, okay, when you propagate along z direction, okay, for example, z inside this whiteboard, the electrical field, okay, electric field is oscillating. If it's linear polarized, the electrical field, has a degree of freedom of where it's pointing to, right? For example, when we quantize the quantized photon, we say that the propagation direction is z, the electric field is of x direction, and then the magnetic field is b direction. But then you can also see other light, okay, where the electric field is at y direction, right, instead of x direction. There's a degree of freedom you can go. Okay, so let's say if we write down this x and y, and then you say, okay, x polarization is 0 state, and then y polarization is 1 state, okay, and where would be this plus and minus state, right? This plus state would be here, right? Just think about it as a vector, right? 0 pointing this, 1 pointing this, and then you have half and half, so that you're pointing 45 degrees on this way. And then where's the minus state, right? The minus state is 0 minus 1, so x minus y, so you get this here. Okay, and then they're perpendicular to each other. So that actually for photon, it's very easy to change your basis. You just rotate your detector 45 degrees, and that's it. Okay. If you don't align your detector x and y, you rotate it. Okay, rotate your entire whatever polarization selection device and then everything. Okay, you rotate 45 degrees, you actually get this measurement on this basis. So for example, in photonic quantum computing, a lot of times people don't use hammer gate, because hammer gate actually need to rotate the qubit. If you ever need to detect, to tell the difference between this plus state and minus state, what you do is you simply rotate your detection equipment, and that way you can actually tell fairly easily. And later we will see that this is actually quite useful in quantum communication. And one thing that I want to mention is that you cannot mix different bases. For example, when you choose plus basis, you already determine what the minus basis is, right? Because the minus basis need to be orthogonal to the plus basis. You cannot say, okay, I measure plus, and I also measure 0. Okay, if you try to do this measurement, just imagine that you're trying to express a number, okay, while the axes are not, perpendicular to each other. And in this case, okay, you will get really, really wrong measurement result. And then, just, don't do it, okay. Any questions? Okay. So previously in the in-person class, I will actually show you the, how to use polarizer of light and then see the, all these different things. But then here with the camera, actually, because the room is very bright, otherwise you wouldn't be able to see me from the camera. Then the room is too bright, actually I can't have polarizer, and then actually you wouldn't be able to see that effect. So if you guys are very interested in that, you can actually search it on YouTube, and then there are actually many of these demonstrated experiment. Now, okay, so we finished a single qubit gate, and now let's move on to the 2 qubit gates. Okay, and 2 qubit gates, just like classical 2-bit gate, is actually the core, okay, for computing, because you're just manipulating 1 bit doesn't really calculate anything. Okay, having 2 qubits interact with each other is the reason that you can have computing. Now, the first thing that let me just write down, okay, what our object is. Okay, you have qubit A, qubit B, and then for simplicity, we say, okay, they're, the electron with ground state and excited state, okay, two of them. They don't have to interact. You can just put them down here. And then the possible state, okay, the possible eigenstate would be four options. One is that, they're both in ground state. Okay, this is a notation. Okay, you have a comma here, and then, first qubit, second qubit. Both of them are on ground state, and then first qubit on excited state, second qubit on excited state, and then both of them excited state. Okay, so there are four options here. And so that to express a 2-qubit, okay, what you do is that you assign 4 coefficients in front of them, right? So you have alpha 0, 0 plus alpha 1, 0 plus alpha 0, 1 plus alpha 1, 1. Okay, and some people will say, okay, these are also 2 individual qubits, and then you can also express the state of this individual qubit as well, right? So can we say that, okay, by describing the state, we can simply describe qubit A and then describe qubit B, okay? So for example, qubit A is in superposition state, okay, and then this notation, okay, this notation here means that this is qubit A, this is qubit B, and that's it, okay, it says that. And then qubit B is also in superposition state, okay, and then let me ask you this. Which one of this is correct? Which one of this is complete? Or the other way is that it can truly express all the 2-qubit states. Maybe show of hands, like you can if this one is correct, describe them one by one. Anyone agree? You can have a thumbnail in the sum up in the in your Zoom. Okay, 1. Okay, how about this one, the top one? Okay, another 1, and then the others are undecided voters, right? So, the correct answer is this one. Okay, it's this one, and the question is that the answer is actually a little bit deep. Is that in classical case, yes, this indeed, if these are classical bit, right, having them separate is the same as having them as a whole. But then for quantum qubits, there's a second concept now. It's called entanglement, which we will actually discuss more later. Is that there are actually information stored, globally, not on individual qubit. I will write down a state, okay, for you guys. For example, if your state is in a superposition between the 0, 0 state and 1, 1 state, okay, 0, 0 state and 1, 1 state. And then you can kind of try to express this, okay, with this, right? If you write them down as individual qubit, and then we can give you a try. If you write things down as individual qubit, then what you will get is that, okay, take this as a simple multiplication, okay, alpha 1, 0, alpha 2, 0. So what you do is you write them down together, alpha 1, alpha 2, okay, 0, 0, right? First qubit at 0, second qubit at 0 is the same as 0.0, right? Just an expression of your state, right? So then if you guys are okay with this, then we replace it with 0, 0, right? Because both qubits are at 0. And then you move on to the next, alpha 1, beta 2, and then it's 0, 1, right? And then beta 1, alpha 2, 1, 0, plus beta 1, beta 2, 1, 1. Okay, and if you look at it, if this has to equal to the state I write down here, then what you need is that alpha 1, beta 2 and beta 1, alpha 2 has to be 0, right? So alpha 1 times beta 2 equal to beta 1 times alpha 2 equal to 0. Okay, so it means for alpha 1 and beta 2, there has to be one term that goes to 0, right? For beta 1, alpha 2, there's also have to be one term goes to 0. Now, if you look at the coefficient in the front, right? If beta 2, let's say if beta 1 goes to 0, then what will happen is that the coefficient in front of 1, 1 goes to 0, right? Goes to 0. And if you pick alpha 1 goes to 0, then the coefficient in front of 0, 0 goes to 0, right? So actually there's no solution, okay? There's no solution if you try to express this state with this notation. What it means is that the quantum state, okay, the quantum state of several qubits is not equal to individual qubit and then put them together. Okay, it's not equivalent. And you would say, okay, in what situation this will happen? Okay, this will happen when these two qubits has interaction. When they interact, they get entangled, they get messed up, mixed together, and then so that you can no longer write them down as independent qubit. Okay, so this is a very, very, critical points difference between classical bit and quantum qubit. And then if you take a further careful look, is that this state, okay, if you try to measure the first qubit, you will get 50% 0, 50% 1. If you try to measure the second qubit, you will also get 50% 0, 50% 1. It looks like you didn't encode any information in it. Okay, so what it means is that if the information about this is created by A interacting with B, then neither of them has the whole information, right? You can only extract the entire information by making a collective measurement of both of them. And we will actually go a little bit deeper into this in a later lecture. But you can kind of sense, okay, where we're going here is that the absolute secure communication, right? Is that if I hold one part and then I send another part to another person, and then even if that gets stolen in the middle of the way, as long as they cannot take the one from me, okay, you can the information will not be lost, right? So we'll talk about this later. And then also a deeper look into this is that here the conflict between these two, between these two notations are not very huge. But then you can now think about if there are n qubit, right? And then for here, okay, n qubit, for this notation, if you write down all the possible eigenstate, there will be actually 2 to the nth, right, possible eigenstates, and then you need 2 to the nth coefficient to describe it. Okay, for example, for n equals 3, you need actually 8 numbers. But then for here, if you just write them down as individual qubit, then you only need to use 2n coefficient, right? Each qubit has 2 coefficient, and then n qubit will have 2n coefficient. So that this is clearly you can see that if you reduce, if you describe your qubit system, if you describe the system by individual qubit, you actually lose information, right? There are a lot of coefficients, there are a lot of information stored in other coefficients which cannot be seen, okay, by just looking at individual qubits. Okay. Any questions? Now let's introduce a very common 2-quantum gate. It's called control NOT gate. Okay. The reason that we talk about control NOT gate is that mathematicians have proven that when you combine a control NOT gate with single qubit gate and then combined with control NOT gate can be used to construct any gate, any quantum gate, right? So that this is sometimes called universal gate, okay, universal quantum gate. For example, the universal gate for classical computer is AND and NOT, right? If you use AND and NOT, you can actually create all the possible logic. And so control NOT gate is called universal gate, and then if you try to build a universal computer, you try to claim that your structure can do universal computing, you have to demonstrate control NOT gate. Okay, and what the control NOT gate is that it uses qubit A as a control to control whether a NOT operation will act on the qubit B. Okay, so for example, if qubit A is at 0 state, then nothing happened. Right? No matter if your second qubit is on 0, then it stays 0. If it's on 1, then it stays 1. Okay, this is 0 means don't do anything. Okay, if your control qubit is on 1, then what you do is that you do a NOT gate on the second qubit. Right? So 0, 1 will be 0, will be 1. Sorry, 1, 0 will be 1, 1. Right? From change 0 to 1. And then 1, 1 will go to 1, 0. Right? This is the definition of control NOT gate. And then why is it a universal gate? We can't prove that here for you. Okay, if you're interested in that, you can Google, and then I'm pretty sure you guys would give it up like in 20 minutes. Okay, it's very tedious mathematical proof. And there's actually a circuit notation, okay, for control NOT gate. That is the good way to, well, the less confusing way to write it is that if this is your first qubit, this is your second qubit, and then use the first qubit as control, you put a solid dot here, okay, and then which qubit you control B, then you draw it to here, and then you draw a box indicating there's a gate here, and then the gate is X, right? The gate is X, meaning that if it's 1, then you do X gate. And then you can actually have other control gate, for example, control phase gate, right? If control is 1, then you flip the phase by 180 degrees. Okay, that's doable. And then you can imagine then X will change to a phase gate here. So that this is a common notation for control gate. And then because control NOT gate is used very, very commonly, so that there's actually a simplified notation for it. It's, okay, control is always the dot, and then which qubit it controls is always straight line here. And then here is that you put a circle here. Okay, I actually don't know why. Okay, but then this is a notation, and okay, we can just accept it, right? And there's as you guys can see that, okay, for any gate, we actually want to express it in a matrix form, right? Because then you don't have to carry over the truth table. Okay, this is called truth table. The idea is that for 2 by 2, okay, 2 by 2, well, for 2 qubit, because there are 4 eigenstates, right? 4 eigenstates, so that your see, so that your matrix will be a 4x4 matrix. Okay, if you have 3 qubit, then you have 8 eigenstates, so that you will be an 8x8 matrix. So that you can see that the complexity level goes exponential. Okay, and then okay, so here what you would do is that you define matrix H11, H12, keep going H14, and then H41, all the way down H44. And then the rest is kind of tedious, but then I would just show you guys the definition. Usually, okay, 0, 0 is defined as 0, 0, well, sorry, it's defined as the first vector, okay? So it's 1, 0, 0, 0, okay, in the vector form. This is just, people prefer to do it that way. And 0, 1 is usually the second one, 1, 0, 0, 0. Sorry, 0, 1, 0, 0. And then 1, 0 is the third one. And then 1, 1 is the final one. Okay, so if by any chance, okay, the matrix you get is different from what you can find online, then usually, okay, if you're very confident about your math, then usually the problem is the definition. Okay, you guys are probably using different definition of the the vector form of the basis, and that could lead to different matrix form. And then if you want to calculate this, then what you do is that you apply this to here and then see, okay, just h on this equal to that, h on this equal to that, and then you have 4 equations, okay, 4 matrix equation, and then for each vector equal to another vector, you will have 4 equations in it because it's a 4x1 vector. So in total, you will have 16 equations, okay, and then you can solve them. And then it's actually not that complicated in this case. Let me write down the solution here. You can look at if you want to see the process of this calculation, you can refer to note page 16 in the note. I wouldn't do it here because that would take up the entire board. So the control NOT gate, okay, in the matrix form is 1, 1. Okay, 1, 1. You can kind of see what's going on here. 1, 1 is just the same as the identity matrix, right? So 1, 1 in the diagonal here just means doing nothing. Okay, and then for here, okay, it becomes off diagonal term. Okay, off diagonal term. Off diagonal term means interaction, because if you apply this, it's off diagonal, meaning that you're converting one vector to another vector, right? So it means that there's interaction. Okay, so this is very common. If there's nothing happen, then it must be diagonal. If there's something interacting, it's off diagonal term. Okay, and for example, okay, if you say that, okay, your first qubit will be used to control the 4th qubit, you don't even need to do any calculation. You can see, okay, this must be some coefficient here, okay, because this is 1, 4 off diagonal, and then because it's because this has to be unitary, then you can kind of see, what it will be here. Sometimes it's the alpha square, alpha conjugate. So there's some quick tricks, okay, to figure out what the matrix will look like. But then for this class, because there's no point to torture you guys, so we will stay in 2 qubit system, so that the maximum amount of matrix you will solve is 4x4, and that's very, very simple. Okay. And then I want to show you guys, okay, what the control NOT gate can be used for, right? So let's work through go through a simple, let's see. Let's go through a simple quantum circuits. And show you guys. Right now, this is the most commonly. Actually, yeah, this is the most commonly used quantum circuits. So there's a qubit A, there's a qubit B, okay, and then qubit A goes through a hammer gate. Qubit B do nothing, and then you have a control NOT gate. Okay, qubit A control qubit B, and then the question is, what is the output? Right, the input state is 0, 0. Right, it's the ground state. Okay, both of them are prepared on ground state. So the way to look at this is that first, qubit A goes through a hammer gate. Right, qubit B do nothing. So you can write down the state here. So just because you have a separate line, okay, indicating different qubit, doesn't mean that you need to write down the qubit separately. Okay, so what you will see here is that, okay, qubit B is just 0, right? It's not doing anything here. Qubit A go from 0 to hammer gate, and then we know that the net result for that is, okay, going into a superposition between 0 and 1 state, right? That's what will happen, okay, if 0 state goes through a hammer gate. And now the second one is that, okay, now we go to a control NOT gate, right? Control NOT gate. So if you're 0, do nothing, right? If you're 0, then do nothing. So we know that the output, one of them is 0, 0, right? The first qubit is 0, second qubit is 0, then do nothing. And the second part is that, okay, the first qubit is 1, right? Then the control gate should flip the qubit B from 0 to 1, right? So that the second component here is this one, 1, 1, right? 1, 1. So that the net result here is that state I just tell you guys, okay, cannot be described by, two separate qubits. Okay, this is the entanglement state. It's actually a maximum entanglement state we'll later talk about. But then this is actually the most widely used quantum circuits, is to have two separate qubits, okay, both at ground state, and then make them into an entanglement state. And then here you can see that, okay, then the control NOT gate, it will be very clear now to see that the control NOT gate is working as qubit A and qubit B interacting with each other. Right? Any questions? Okay. So I want to have a quick summary of the qubit gates, and then you can actually, although we just introduced single qubit gate and two qubit gates, you can actually go beyond that, and then you can create your own gate as long as they're unitary. So first is a single qubit gate. If you want to build it physically, what you need is that you need the ability to control the qubit, right? For example, can you put it on ground state? Can you put it on excited state? Can you flip it to superposition, right? So usually it means that you need to apply voltage, laser, electrical field onto whatever qubit you have, and then change its state. Okay, that's what people do with single qubit gate. And then multiple qubit gate, in general, meaning that you need interaction, okay, between different qubits. And then I don't know if you guys remember, and this actually is a huge problem, is that, for example, you have okay, qubit A here, and then qubit B here, and then qubit C here, okay? And you say, okay, I want an algorithm to use qubit A to control qubit C, right? You want to have a control NOT gate from A to C. But then A and C are physically separated by qubit B. How can you make qubit A and qubit C to interact? Okay, this is not a trivial question. And then if you look at the structure of Google's quantum computer and then IBM's quantum computer, what they have, the structure there is that each qubit would have 4 nearby neighbors, and then this qubit can only interact with these 4 neighbors. Okay, it cannot interact with more, and then go through here and then this. So you can immediately tell that this is not a universal quantum computer, because you cannot have, let's say A is the control qubit, you cannot make it arbitrarily control any bit, another qubit. You cannot do that, right? So that because limited by this physical structure, how to use it to computing is actually a very difficult problem, and then worth looking into. And then there are actually, I don't know, thousands of theory paper proposed how to use this to computing. And then for any physical system, there will be constraints. Okay, and then it's not clear right now how to overcome them to get to universal computing. Okay, and that is all for today.